All right, so the last section in, not the last section, type of integration techniques is in section 6.12, which is using linear partial fractions. So this is another way of breaking down a function so that we can utilize a different, something that we already know for integration. So in this section, you'll see a method for rewriting, right, certain rational functions. That is very useful in integration, as well as other applications. So we begin with this simple observation. You guys know that when we have, right, when we have a problem that's 3 over x plus 2 minus 2 over x minus 5, we can combine it. We can combine it by multiplying the 3 over x plus 2 by x minus 5 on the top and the bottom to get a common denominator. And the 2 gets multiplied by x plus 2 on the top and the bottom, right? And we get a common denominator. And once that happens, you end up with a rational function of x minus 19 over x squared minus 3x minus 10. Well, partial fraction decomposition is when you have something that like this, and you notice that this is bigger on the bottom, which is Bobo, right? So this is the one that you cannot divide. I know I made that mistake in class. So this is the one that you cannot divide, but you got Bobo. And we're basically gonna break it back down. Instead of combining, getting a common denominator, we're gonna break it back down. So that's basically what we're doing. We have a rational function that looks like this, and we are gonna break it down into its individual parts before it was together. And that way, because we have two linear denominators, we can use our integration of ln, right? Because we know that the integral of 1 over u is equal to ln of u divided by the derivative of u. And we'll come back to that derivative a little bit later. All right. So the second integrand is called a partial fraction decomposition. So this part right here where we broke it down, that's what's called the partial fraction decomposition. More generally, if the three factors, ax plus b, and ax plus b, three different factors, are all distinct, none is a constant multiple of the other, right? You have linear factors. That is important. You have linear factors. Then we can rewrite this as a over ax plus b and b over ax plus b to basically, and then solve and use that to solve for a and b using algebra. So for some choices of constants a and b, the more distinct linear factors the denominator has, so weird, it's 100% charged, whatever. The more fractions we'll have. So partial fractions, distinct linear factors. So here is an example. So you have Bobo. You cannot divide. So I'm going to focus in on just the algebra for a second. So I'm going to forget that I am integrating, and I'm going to focus on this. So I'm going to take the 1 over x squared plus x minus 2. And what I want to do is I want to decompose this. So before I can decompose this, I need to factor the denominator and see how many denominators I'm going to end up with. So of course, with the x box method, when you factor this guy, you end up with x plus 2 and x minus 1. So now we have our two factors, linear factors. That is what is important. And we're going to add them together. Now the question is what was the numerator before all of this, right? So if I set this up and I want to solve for A and B. So I want this to equal this. And that will help me figure out what is A and B. And I'm just going to use algebra. Okay? So first off, if I was to multiply this whole entire thing by x plus 2, x minus 2, right? Which basically means you're going to distribute x plus 2, x minus 2 to everybody. Well, when I distribute x plus 2, x minus 2 here, this actually does cancel out the denominator, so we are left with just 1. When I distribute it here, and I guess I'll show all of the work on the first one, okay? So we have x plus 2, x minus 2 over x squared plus x minus 2 equals A times x plus 2, x minus 2 over x plus 2 plus B times x plus 2, and this is a 1, sorry, that is supposed to be a 1, x plus 2, x minus 1 over x minus 1. And you notice that that will cancel out with the denominator if I was to factor it down, so we're left with just 1. Here, the x plus 2's cancel out, and you're left with A times x minus 1. And here, the x minus 1's are canceled, and you're left with B times x plus 2. So how can we solve this algebraically? Well, we're going to use a little trick, okay? When x is equal to 1, what do you notice happens? Okay? When x is equal to 1, I basically am able to eliminate A, because 1 minus 1 is 0. So 0 times A, that goes away. So when x equals 1, I'm able to solve for B. And B ends up being 1/3. Now, to solve for A, I need to let x be -2. Okay? And now I have 1 equals A times -2 minus 1 plus B times -2 plus 2. And you notice that that cancels out the B. And we're left with 1 equals -2 minus 1, which is -3. So A is -1/3. Now, I did all of this math because I want to rewrite this guy. So you notice how I have B is 1/3, A is -1/3. So now the new integral that I am solving for is A over, which A is -1/3 over x plus 2, plus B, which is 1/3 over x minus 1. And you have to leave it like this. the negative 1/3 and the 1/3. You do not want to simplify this and take out, like rewrite it as negative 1/3 times, right? Flip the guy and multiply. Don't simplify this. Leave it as is, because the A is what's important and the B is what's important. So now we know that when we integrate this, I can take out the coefficient of negative 1/3, and I'm left with 1 over x plus 2 dx, plus take out the 1/3 of the second guy and integrate just 1 over x minus 1 dx. Because this is added, I can simplify that. And this should be an easy integral. So now we got negative 1/3. Well, this is a linear term, right? It is just 1 over u. And we know that the integral of 1 over u is just ln of that u, divided by the derivative of the inside stuff, but the inside stuff is just x plus 2. So it's just the derivative of x, which is 1, plus 1/3 ln of u for the second guy as well, divided by 1, which of course doesn't matter, and plus c, and you're done. Now, as a, just for purposes of multiple choice answers, if this is an FRQ, you would stop right here. If this was a multiple choice question, you might see this where they use the properties of logs and they put all of this stuff together. So if you remember the properties of logs, that 1/3, can come up here. That positive 1/3 can come up here. So this becomes ln of x plus 2 raised to the negative 1/3. And this is plus ln of x minus 1 raised to the 1/3. Okay. And then once they clean this up, you have two ln's. So you can combine those two, right? So this becomes ln of x minus 1 to the 1/3 divided by x plus 2 to the 1/3. Made that a positive by taking it to the denominator. Okay, and the last step is just becomes the cube root. So ln of the cube root of x minus 1 over x plus 2 plus c, cube root. Okay, so different ways of seeing it as a multiple choice. So in this next problem, we have 3 distinct linear factors. Okay, so again, this is Bobo. Bobo should tell you linear partial fraction decomposition, PFD. So with partial fraction decomposition, you want to take that denominator and you want to break it up. So you have your 3x squared So let's break this up algebraically. So we first we factor out an x. We're left with x squared minus 1. And then, of course, that x squared minus 1 is difference of squares. So we got x minus 1, x plus 1. And these are 3 distinct linear factors. So now the rewrite to figure out our a, b, and c, you'll see why there's a c in just a second, is 3x squared minus 7x minus 2 over x times x minus 1 times x plus 1. Okay, that's the breakdown of this, is equal to, because we have 3 distinct linear factors, I need to break this up into 3 linear factors. So we got a over x plus b over x minus 1 plus c over x plus 1. So this is the partial fraction decomposition. Next up, I got to solve for a, b, and c. So in order to solve a, b, and c, again, I'm going to multiply both sides by that denominator. And when I do that, and I distribute it, I'm left with 3x squared minus 7x minus 2 equals, the x cancels out, but you're left with x minus 1, x plus 1, plus b. Here, x minus 1 goes away, right? But you're left with x and x plus 1. And then for c, x plus 1 goes away, but you're left with x and x minus 1. So this is the equation that I'm going to use to help me solve for a, b, and c. So again, I look at the factors, right? There are three possibilities. I'm going to let x equal 1, because that's one of my answers from that denominator. I'm going to let x equal 0, because that comes from that. And I'm going to let x equal negative 1, because that comes from that factor. So when you do that, it actually helps you solve a, b, and c. Okay? So when we let x equal 1, we're going to plug in. That means you're going to plug in 1 everywhere for x. So this part, when you let x equal 1, should be 3 minus 7 minus 2. 3 minus 7 minus 2 equals, when you let x equal 1, this whole thing, the a part, does disappear. The b part does turn into 2b, right? Because you got b times 1 times 2, so that equals 2b. And the c does go away as well, because here you got 1 minus 1 is 0. 0 times anything is just 0. So 3 minus 7 minus 2, you end up solving this, and you got b equals negative 3. Next up, let's let x equal 0. So when you let x equal 0, guess who goes away? The b and the c, right? Anywhere that x is there, it's going to go away. But I'm going to take that 0 and I'm going to plug it in everywhere for x. So when you plug in 0, you've got negative 2 equals 0 minus 1 is negative 1. 0 plus 1 is 1. So we got a times negative 1 times 1. So negative 2 is equal to negative a. So a is equal to 2. And then the last step, when you let the x equal negative 1, you end up with 3 plus 7 minus 2 equals c times negative 1 times negative 2. And so you have c equals 4. Once you have your a, b, and c, the rest is pretty straightforward, because you can break this guy up into, so this whole thing now has been partial fraction decomposed into, we said a is 2, so 2 over x minus 3 over x minus 1 plus 4 over x plus 1. And remember, once you break these up, you can integrate each one individually. So I'm just going to take out a 2, and this is going to be ln of x, minus, I'm going to take out a 3, ln of x minus 1. And I'm going to take out a 4 ln of x plus 1. Now, because all of these were just x, I didn't have to divide by any derivatives. I didn't have to apply the chain rule. And then plus c. And remember, with multiple choice answers, they could use the log properties to combine all of this, where this becomes a power, and then putting everything together. Now, a few things that I do want to say, we'll talk about it in class, is sometimes these absolute values could disappear. Okay? So ln of x squared, for example, will never be negative. So I don't need an absolute value here to show that. Okay. Example 3. This is one of those problems where you look at this and you see that this is bigger on top, right? Bigger on top means I can simplify this using long division. So I'm going to save you the steps. When you use long division, hopefully, you have figured all of that out. I'm not going to show the steps for long division just because I don't have the space on my notes. But once you first use long division, you end up with a problem that looks like this. You got the integral of 2x minus x plus 5, because that was our remainder from the division problem, over x squared minus 2x minus 8. And then here is an example where, okay, I'm almost there, right? This, easily I can integrate that. But then this guy right here, I need a little bit more work. So this part, you notice, is Bobo. And when you have Bobo, you have partial fraction decomposition. This integral can come along for the ride if it wants, or I can just integrate it right now. This is going to be 2x squared divided by 2. So the answer is just going to be x squared for that part, right? So that's done. Now I need to just integrate that x. I'm going to take out the negative. Or you know what? I'm not going to take out the negative because I'm just going to put it right here. So now I need to just integrate the x plus 5 over x squared minus 2x minus 8. So again, partial fraction decomposition, right? You got to factor this guy down. So when you factor it down, you end up with x plus 5 is over x minus 4 times x plus 2. Because we have two linear factors, I need to solve for a that goes with x minus 4 plus b that goes with x plus 2. Now, does it matter which one a is with and which one b is with? No, because multiplication is commutative. Some of you could have put x plus 2 times x minus 4. The goal is here, though, once you multiply the whole entire thing algebraically by x minus 4, x plus 2, you should end up with x plus 5 is equal to a times x plus 2 plus b times x minus 4. Now, our factors, right, our solutions from our factors that will cause the denominator to not work is let's let x equal negative 2 and let's let x equal 4. And once you do that, when you let x equal negative 2 plus 5 is negative 3, and that equals, the a is gone, right? And so that equals negative 6b. So b is negative 1/2. And then when you let x equal 4, you've got 9 equals 6b, and the b is gone. Or 6a, sorry. And the b is gone. So a, once you simplify, is equal to 3/2. So now it is easy to integrate ln of, remember, I've already integrated that, so I'm done with that. So, and I got the minus because I ignored it in this problem. So we've got a is 3/2 over x minus 4 plus b, which is 1/2 over x plus 2. So when you integrate, final answer, you got your x squared minus 3/2. Remember, that minus sign goes to all of this, please, so don't forget that, okay? So it's going to be minus 3/2 ln of x minus 4 plus 1/2 ln of x plus 2 plus c. Oh, that's a minus. Okay. All right, so perhaps you're wondering what happens when the denominator of rational contains repeated linear factors such as x minus 1 squared. Well, in this case, the decomposition looks like the following. If the degree of p of x is less than n, then we can write it, if the degree of p of x is less than n, okay, so if it's bigger on the top, then we can rewrite it like so. So as long as it's 1 degree. So the thing is with these types of problems, they are not going to be covered on the AP Calc BC exam. Everything that is covered on the BC exam is just what I just did with you with the first 2 problems. So again, it's a nice to know. It's not a need to know. For those types of problems, so we're not going to worry about it. Okay. Now, example 4. I'm not going to do it in this video. Quadratic factors. Again, these problems will be covered in class but not appear on the AP Calc exam. Unfortunately, because of the timing for this year, I'm not going to do them in class either. So, again, these are a nice to know. It's not a need to know, so we're not going to do this. Yeah. No. You can scan that QR code to see, the video solution for example 6 when you have quadratic factors. The only difference when you have quadratic factors is that up top you'll have, instead of a constant, you're going to have a linear factor when you have a quadratic factor in the denominator. So I'm not going to go over these because they will not be on the AP exam. All right, now that you've discovered this new integration technique, keep this in mind. Not all rational functions will require partial fractions, right? You remember that When it's bigger on the bottom, most likely it's going to be partial fractions. But if it's bigger on the bottom like this, you can do partial fractions. Unfortunately, what if it doesn't factor? So try to do these two types of problems, and then we'll talk about them in class tomorrow.